Hello everyone. So can someone confirm whether I am audible? Okay, sorry for the delay. So let's start. So okay, we have already 26 participants. So you can start. So greetings to everyone. So today we have day two of mass spectrometry workshop. So today mostly we will talk about ionization technique and mass analyzer and also detector, and then some variety of different mass spectrometer. Okay. So if you have question, please write in chat box. Okay. So this is the outline of today. So we will first talk about ionization techniques and then mass analyzer and detection, and then we will move to mass spectrometers. So let's go to part one. So as yesterday we already talked about this. So we have a sample in mass spectrometry, and then samples will be introduced to ionization source. So and then mass analyzer, and it will go to detector, right? So okay, so these are the ionization technique that I discussed yesterday, right? So there are different kinds. So like gas phase ionization, spray based ionization, atmospheric pressure ionization, and desorption ionization. Okay, so we can use different types of ionization method, and if you see, different types of ionization method can be used for different compounds. Okay, and also mass range that it can like analyze by mass spectrometer, it can vary. Okay, so different one will have different mass range. Okay. Okay, so this one is okay. Am I audible now? Please confirm. Someone is saying I'm not audible. Okay. So if my voice is either low or very high, please let me know. Okay. Okay. So this is the first ionization technique. So I think this is maybe historically also this is first one. So this is called electron ionization. Also, we can call it EI, and also we can call it electron impact ionization. Okay. So in this case, what happens is first gaseous sample will go inside your mass ionization chamber. Okay. So you see there is like this is ionization chamber. Okay, and this you see on right side, this is mass analyzer. Okay. Okay, so first your gas sample will go. Okay, and because you have here some tungsten film, as yesterday we talked, it will because you have you are heating this tungsten film. So what will happen, some electron will be released, and because you have some difference in potential, so what's going to happen, this electron will release and it will move towards in a vertical direction. And because anode is here, so what will happen, anode is going to collect these electrons. Okay, anode will collect this electron because this is positive charge. Okay, this is positive charge. Okay, so this will collect the you can say with respect to this one, this is more positively charged. Okay, anode is more positively charged with respect to G1 and G2. So G1 and G2 is just metal plate which is at different potential. So what will happen? So when gaseous sample is moving inside and some uh, electron beam is coming, so it will hit, and then your molecule will be ionized. Okay, because the energy of that electron beams, as we talked yesterday, it is 20 around 70 electron volt. Okay, so now after that it will move to another slit. Okay, so it will move to this slit where your mass analyzer will be there. Okay, like so you have mass analyzer here. Okay, so what in this region, what's happening? This is called accelerator chamber. Okay, so you will have different plates because you're now analyte all are molecular ion or fragment ion, so they will go inside and then they will see potential difference. Okay, so because of this difference in potential, what will happen? This positive charge will be more attract inside. Okay, and then once it catch some like have enough kinetic energy, then it will be sent to mass analyzer. Okay, so okay. Okay, so this is the diagram for electron annihilation. So you see, your analyte in gaseous form, they are going inside, and you have this electron beams. Okay, electron beams are there. So what will happen? Your analytes will get ionized. Okay, and these ionites, if they are unstable, what will happen? These analytes, which is in ion form, they will also get fragmented. Okay, and all of them will be going towards mass analyzer. Okay, so you see these acceleration chamber, so we can also call it focusing lines. Okay, so lenses, sorry, focusing lenses. Okay, so this will help in focus all your analytes to move into the mass analyzer. Okay, so it will not go and hit on the surface here and there. Okay, so Bhanu is asking, can I explain acceleration chamber again? Oh, okay. Yeah. So see, acceleration chamber is just as I talked here, when suppose this one tungsten film, you heat this tungsten film and some electron is coming out, right? Now these electrons, because of this, different metal plates having different potential, what's going to happen? This will move to more positive charge, right? More positive, potential. So that's why it is moving this direction, right? Now suppose you have this positive charge, okay? Your molecular ion has positive charge, okay? So what will happen if once it goes inside and it will see the difference? This is plus, suppose actually, writing plus minus is also not necessary. We can write like this. Like we can write plus 30 volt. Maybe this one is plus 20 volt. This one is plus 10 volt. Okay, so what's going to happen? Your this positive charge, they will try to go to lower potential. Okay, because positive will prefer lower potential. Okay, so it will start moving, and then that's how they will obtain some kinetic energy so that it can move to mass analyzer. Okay, so I hope you understand. So it's just difference in potential. Okay, so that's how this positive charge is moving. Okay, so in the electron ionization problem is it is that those electron beam, they are having very high energy. So sometimes what happens is because of that very high energy, our molecule will be fragmented very easily. Okay, so suppose you have some molecule, you want to study this molecule. Okay, so if you want to study this molecule, you will prefer to have molecular ion peak. Okay, you will prefer to have this. But what happens if you use EI ionization method? So what's going to happen? This molecular ion peak will very fast fragmented into M1, maybe M1, M2, M3. So if you get the spectra, you will get a spectra, okay? But you may not get this peak, a molecular ion peak. You may not get, okay? So that is the disadvantage of EI, okay, electron ionization method. Okay, so that's why this people are like inventing various kind of new ionization techniques. So there is another one is chemical ionization. So in this method, what's happening is instead of gaseous sample when it is going inside, they are also putting some reagent gas. Okay, like you can have CS, this methane, or you can have ammonia, right? NH3 ammonia. So you can have different kind of gas. So now what will happen? These gas, because they are in large amount, okay, so they will because again you have filament, okay, you have some filament which will release the electron, right? So electron will be released, and then these gas, they will be ionized because they are very small in size, right? So they will be very easily ionized, okay? So once they ionize, then these ionized, this reagent gas, they will hit on the gaseous sample, okay, when they come inside, okay. And then because this is reactive, it becomes reactive when they are in ion form. So they will make this gaseous sample also ionized, okay. So here I have given the example. So because suppose you have a CH4, and then CH4 maybe release CH3 free radical, and then you may also have this H plus also you can have, and maybe we should have here, we can say minus maybe. And then this H plus, if it is there, then this CH4 plus H plus, it will change to CH5 plus, okay. So there are variety of reaction will happen. So some of them will be CH5 plus. And now because this is highly reactive, so what will happen when this hit on the this molecule, any analyte, what will happen? One proton will transfer from this to here. So your molecule, suppose molecular weight is 256, suppose. So what's going to happen when hydrogen is attached? Its molecular peak will be 257. Okay, and this is so this is easy to detect. Okay, uh, so in this chemical ionization method, we can say it is soft ionization method. Okay. So there is another method, another also type possible. So your CH4, that any reagent gas, they can change to C2H5 plus, and then they will react with our molecule analyte, any whatever we want to measure the spectra, mass spectra. And we can also create this one. Okay, we can generate this one. Okay, so we can generate a M minus H plus. Okay, so you see, we are not removing the electron from molecule, but we are attaching some proton. Okay, so it's called soft ionization method. And because now it becomes ionic, you can easily measure the mass of this uh, analyte. Okay, that is in ion form. Okay, and also I would like to say, you see, sometimes you will see magnet, right? So what is the need of these magnets? So please understand, uh, if suppose electron beams are generated, so they should have some purpose to move, right? Like they will maybe randomly move. So we have to, we want them to, like move, like in control manner maybe. So if, because this is suppose electron is charged already, and you put some magnet, what will happen? Because of as I told, because of Lorentz force in the magnetic field, what will happen? These electron beams will be, yeah, they will be like more like moving easily, like we can control their direction. Okay, so please understand what is the purpose of these magnets. So sometimes you will observe that. Okay, so you can also have the electrophilic addition. So you have, suppose, this methyl cation, and then you have some analyte, which can also make the adduct. Okay, so if you might observe, if when you use this CI method, so and suppose you got some spectra and you have this M here, you may get this M plus 15. So 15 is molecular mass of this CS3. Okay, so we should know these things. Okay, so sometimes if we use different method, we should know like what method we are using and why that peak has appeared. Okay, so okay, so this is, yeah, chemical ionization. So what's happening in chemical ionization? We are sending analyte inside, okay, and also we are sending some. Here you see they have used chlorine gas, okay. So there you can use variety of different gas, and you put some reagent gas inside, and now because you have some filament, right? Because of this filament, what will happen? Some electron will be released, and then you see this will hit on the reagent gas, and then what will happen? This reagent gas will ionized, and then also your analyte, because they will hit each other, and they will also be analyte will be also ionized, and then you will get your ions which will move to mass analyzer. Okay. Okay. And so, it is not possible all the time that we get the gaseous, sample, right? So some molecule may have very high boiling point, right? And they may not even evaporate, right? So how can we get their, mass spectra, mass analysis, we can say. So that's why scientists have developed, field desorption method. Okay. So in this case, what's happening? You have some kind of, you can say some kind of anode. Okay, so you have some metal plate, okay, which is like acting as a anode. Okay, and you have some carbon microneedle. Okay, you see these are sharp, this is like a maybe like this carbon microneedle. So what's going to happen if suppose I put my, like suppose not here. What I mean is, if suppose I put my sample on this, okay, on this surface, some solid surface, solid analyte, okay, I put on the surface, and because it is, anode, what's going to happen? Some of the electron will easily go to anode, okay, easily it will transfer from your molecule sample, okay. So you see, you must be wondering why it is happening. So this is called quantum phenomena, okay? Quantum tunneling, okay? So because of, if you suppose mm, you have some sample in your petri dish, and you have this plate, okay, metal plate, you just take out from your mass spectrometer, and it has a lot of, sharp needle. What you do, you just take this sample little bit and put it here, okay. And when you put this plate inside your mass spectrometer, and you like start analyzing your sample, you say, so you applied this voltage, like negative, positive voltage, right? So because of this positive, too much positive, very high positive voltage, what's going to happen? Some few electrons, it will go to your anode, okay, and then your molecule will be ionized, okay. And once it is ionized, it will, because of, we will have potential gradient and all, like we will have different potential gradient, and this molecule will start moving to mass analyzer, okay. So yeah, one is simple, one electron will be removed, and another is also sometimes we can get the sodium adduct. Okay, just like previously I talked. So these sodiums, it may comes from, like what to say, if you suppose this plate has some, what to say, some sodium, some impurity or something, so then you may get also, or some salt is there in your material, then you can get this kind of adduct. Okay, so you should know like what kind of material you are using for your, analysis. Okay, so okay. Okay, so uh, there is, I talked about field desorption, right? So there is also field ionization. So field ionization is just like, you can say maybe just like EI, but it's quite different actually. So what is the difference? In field ionization, you have some gaseous molecule, and you have some arc, some kind of which will have very high, potential. Okay, very high potential, and like what you say, uh, arc discharge. Okay, so what will happen when this gaseous molecule hit on this, this arc? What's going to happen? Because it is having, very high positive voltage. So your analytes. Okay, 1 minute. Okay, so these analytes, they will get also ionized. Okay, and once they are ionized, as we will have some accelerator chamber, and then what will happen? This will move to mass analyzer site. Okay, Okay, so uh, there is a difference between field ionization and field desorption. So as I already told, in field desorption, what you need to do, you can use some solid sample, right? So what is the purpose? So purpose is in field ionization we can ionize the gaseous molecule, and in field desorption we can ionize non-volatile and thermally labile compound. Okay, so you can understand they are like solid. Okay, and also mostly it could be polymer like biomolecules and all. And sample state we already talked. They are in field ionization it should be gaseous phase, and in field desorption it could be solid or liquid. Okay, so we will just transfer them to emitter, that anode plate. And yeah, so mechanism is same, that high electric field is, you are applying very high electric field near emitter, okay, so which will strip electron, okay, electron will be removed easily. And similarly, here also you apply high field, which will cause ion ejection from emitter. Okay, so it's both are actually quite similar in the mechanism. And yeah, ionization type is this is soft ionization because it's not you are not applying, you are not hitting with electron beam of very high energy. Okay, so it's like one molecule is coming nearby this high electric field, and they will just because of quantum tunneling, one electron will be moved and they will be ionized. Okay. Okay, so there is another one, this electro spray ionization, which is also soft ionization technique. So, uh, in this all, this is actually very popular, and in 2002, yeah, two scientists have got Nobel Prize. So this is soft ionization, means fragmentation won't be too much, okay, and it works very good with polar molecule and large biomolecules, okay. Okay, and also you can you can get multiple charged ions. Okay, so we will talk about this. Okay, and yeah, it is coupled with a LCMS more often. And there are two types. So actually, in all the mass spectrometer, we can have two types. So positive mode and negative mode. So positive mode and negative mode is just if you have M. Suppose you have any analyte with a molecular weight M. So if it is changing to M plus, then it is called positive mode. Okay. So if it is changing to M plus and it is going to mass analyzer and then getting detected, then it is called positive mode. And if suppose M is changing to M minus, okay, and then it is going to mass analyzer and then it is going to detector and analyze, it is called negative mode. So please understand, this is very, because sometimes when you do this experiment and you go to yeah, like people who handle mass spectrometer, and they may ask you, do you want to do positive mode and negative mode? You, if you are not sure, you just say you want to do both. Okay, or you can first do positive mode, and you see if you get molecular ion peak, then you don't need to do negative mode. Okay, so if you don't get molecular ion peak in positive mode, then you can go for negative mode also. And also if you are suppose you didn't get molecular ion peak in your mass spectra, then you can use another instrument of mass spectrometer. Like sometimes you can use multi-top, sometimes you can use what to say, uh, different kind of like fab, fast atomic bombardment mass we can use, HRMS we can use. So there are different variety, right? Okay, so what happens in ESI? So in ESI, you see, you have some various, like needle, okay? And what you do in needle, you apply some voltage, potential, okay? You apply some potential, okay? In needle itself. And now you are inserting your sample. So you are inserting your sample, suppose your sample analyte, and also you have some solvent, okay, and you insert them inside. So what will happen, because solvent will be more, right? So analyte will be but surrounded by your solvent, right? So suppose this is solvent. So okay, and then it is going inside, and now tip is very narrow. Okay, so they will become very small particle. But now you see, because this tip, this needle, you can say, this is having very high potential. So what's going to happen? Your solvent, the solvent you are using, they will easily, like we are using such solvent only. Okay, so they get ionized easily. Okay, so because of that, it can, it will get, you see, here I have shown positive charge. So even though it comes from this capillary needle, it becomes ionized. Okay, okay, it is becoming ionized, and then it is moving. Why it is moving? You see, we have applied the voltage. Okay, so here you have positive voltage, and here you have negative voltage. So if you see positive, negative is, I think I sometimes worry. So it may be misunderstanding. So it will be like this. Okay, it will be like this. Okay, so you don't need a very large opening. Okay, so this is very small slit. Okay, this is very small slit, and you have positive, maybe negative charge here. Okay, and here you have positive charge. Okay, so what will happen now when your molecule come from this slit, and they will go to here. Okay, because of this difference. Okay, and then it will go to mass analyzer. Okay. Okay, so someone is asking me question, do we have positive and negative mode in EI analysis? Maybe it's hard, because when we hit with, this electron beam, mostly we will get a molecular ion in positive mode, like mostly it will be positive. So I think, E, yeah, in EI ionization, it is hard to get negative, negative, what to say, you can say charge, negative charge, okay? But it may be possible, like suppose you get some molecule is there, like maybe you got AB, suppose you got AB, okay, and now you ionize this, and then you have AB, maybe this one, and then suppose what happens after you got A plus, and then you got B, and suppose this fragment, or yeah, fragment is not so stable. It may change into, like maybe A minus, and like maybe we can just consider, okay, A1 minus and A2 plus plus, something like that, so there are different possibilities. So but it is hard. Okay, so yeah, Santosh is asking, is there any special criteria while selecting the solvent, like you should not some salt with our design? Yeah, actually salt is not good for ESI method. Okay, so yeah, so you should find some solvent which is mostly people use polar solvent. Okay, yeah, mostly people use polar solvent. So Anisa is asking, ESI is used in. I will talk about tandem mass spectrometry. Okay, so someone asking, is there any website instruction which fragmentation ion will form? Uh, it's I think it's available, but it's not easy to get the exact fragmentation. Okay, so yeah, it's not yes. So anyway, let's move. Okay, so someone is asking me how sodium adduct is formed. So yeah, I was telling. So sometimes there will be some salt. Okay, some salt, or there will be some what to say, like suppose you made your sample, and you have some sodium chloride, or some kind of sodium salt. Okay, so you can get the sodium adduct also. Okay, so it's not need to be just like sodium. It could be any other impurity or something. Okay, so it's possible. Okay, so you have to know these things. Okay, but of course, if your system is having no sodium, then you cannot get adduct with sodium. Okay. Okay, so here I'm showing you example. Suppose you have some micro needle, and you are putting your if you are putting your solvent inside, and suppose you didn't apply any voltage. Okay, then what's going to happen? This solvent will just fall. Okay. Okay. So here you see we have applied the voltage. That's why your solve uh, this analyte with solvent, they are moving, and you will observe. So uh, you will observe, we are not just inserting these. Okay, we are also having the some nitrogen gas purging. Okay, they are called, we have like nebulizer gas, and then also we have a kind of nebulizing gas, and then we have drying gas. Okay, we have drying gas. So what will happen? You are purging with this drying gas and nebulizing gas. What will happen? Your solvent will dry. So suppose you had very big, the particle with this molecule is inside, and then you have some solvent. Okay, there are many solvent, right? All solvent, and now you are drying with your nitrogen gas. Then what's going to happen? Size will decrease, and when size decrease, what's going to happen? Charge you see that will be transferred to this molecule. Okay, so you see here, but now what will happen when it is, like suppose lot of charge is generating. So they will have, repulsion between each other. Okay, so they can, move, what to say, yeah, they can be, easily separate. Okay, and they can go inside this mass analyzer. Okay, so someone is asking, usually why we see carboxylic acid in negative mode in mass spec but not in the positive mode ionization method. Okay, see, so usually when we see, yeah. See, that means, in negative mode, your carboxylic acid is stable, but in positive mode it is not stable. Okay, so I think, you can, yeah, if you can look at your molecule, and then maybe you can decide which one, which mode you have to do. So mostly people do positive mode. Okay, so but we can change it. Sometimes we may not get in positive mode, so we can change to negative mode. Okay, maybe I will talk about that. Okay, so I think tomorrow maybe I will talk about that positive and negative mode. Okay. Okay, so you have, yeah, ESI. So you see you have this sample solution is going inside, and you have some nebulizing gas, and you have also, drying gas which is going inside. And what's happening? Your solvent will dry, and then analyze, so some charge is there, and that's how your molecule will get ionized, and then it will go to mass analyzer. Okay. Okay, so what is the, so someone was asking me yesterday, what is the limit for mass spectrometer? Like, what could be the highest molecular weight that we can measure? Okay, so I find these two paper. I think it is in, 1995. Okay, so both are like around 1994, 1995. So scientists have in this one, they have find, very large single molecule ion, and here you can see they have analyzed this coliphage T4 DNA. Okay, and their mass is 10 to the power 8 Dalton. So you can imagine it's very high, right? So okay. Actually, mass spectrometry, it's not so, like, what to say. Uh, of course, if in your lab you have many mass spectrometer, then yeah, you need to think about that. But most of the time, I see we don't have so many mass spectrometer in same lab. Okay, so yeah, whatever you have, you can just go for that. Okay, and then see whether you are getting molecular ion peak or not. So best, if you ask me best ionization method, I can say, yeah, ESI is best. Okay, ESI or multi is best. Okay, so you can go for, soft, always, soft ionization method is best. Okay, because it will give you most probably it will give you the molecular ion peak. But if you go for EI, you may not get. Okay. Okay. So in ESI, you don't have any, size limit. Okay, so ESI can ionize very huge molecules. So I have shown here example. Okay, so this is also soft ionization. So that means it can also preserve non-covalent complex. Okay, so suppose protein. The non-covalent complex means, suppose in protein there is one protein which is having very complicated structure, and then another protein having, and they are having some non-covalent interaction between them. Okay, so even these overall molecule can be analyzed with ESI. So you can understand. Okay, it's how useful it is. Okay, actually there are a lot of questions, but I want to complete so many things today. So Maybe I can take question like every 30 minutes, maybe. Maybe it's the I will stop that time and I can answer the question. A lot of questions are there. So why peptide always analyzed using ESI positive mode? How can we analyze DNA using MS? It has so many charges. Does all the charge moiety of DNA get ionized by ESI techniques? See, when you are saying DNA is ionized, I think we should not say that. What you can say that, see, overall your DNA will be neutral molecule, right? Your DNA will be neutral molecule. What you are saying that there could be some zwitter ion, right? There could be like there is some plus charge and then there is some minus charge, right? But overall they are neutral, right? So what we are talking is like we don't need to care about what charge is having. Okay, what we need to see is that whether it is ionized or not, like it is having excess charge. Okay, so if it is having excess charge, like then you can analyze by mass analyzer. Okay, but if it is neutral, like overall charge is zero, then yeah, you have to go, you have to first ionize it. Okay. Okay, so yeah, you can see if you use this ESI method, it can also maintain structure and function. Okay, so you can understand how important this method is. So if you combine this with HPLC or capillary electrophoresis, okay, so it you can get a very, yeah, even for complex biological mixture, you can get yeah, mass analysis. Okay. Okay, so there is another one, thermo spray ionization, which is called TSI. So just similarly like ESI, but in this case there is a solvent flow. Okay, and it is instead of having charge, it is having heated capillary. Okay, so because of this heated capillary, that's why it is called thermo spray. Okay, so because of this heated capillary, what will happen? Your solvent will evaporate. Okay, and solvent will evaporate, and then your this you have some, like what we talked in a field ionization, right? You have some electrode which is having, some discharge, and then what will happen when your molecule is coming nearby, it will get ionized. Okay, and then it will move to mass spectrometer. Okay, so it's just like, electro spray method. Yeah, Guru is yeah, telling is correct. So yeah, I think if people can write question in the, this question and answer, it will be good. Okay, so I can, answer it later also. So yeah, try to, if you see next to chat, you will find question and answer. Okay, just go there and you can submit your, just copy paste whatever you have typed. Okay, so later I can answer it. Okay. Okay, so yeah, so you have liquid sample and you are using heated capillary. Okay, so because the heated capillary is there, so you will get some aerosol, your particle will be inside, and then it will, similarly it will produce different ions. Okay, so yeah, this also works well with HPLCs, and also this is soft ionization. Okay, just like ESI. Okay, so yeah, so just like ESI, there is a MALDI. So two method is very popular. Okay, MALDI and ESI. So in MALDI, what we do, mm, if you see here, you see here, okay. So we have some metal plate, okay. We have some plate, okay, and we use our sample, and then we use some matrix. Matrix is just some, molecule, okay, some viscous molecule, you can say, okay, viscous material. And what you do, you mix them, you see, and you see these spot, you see these spots. They are just like a, you can say like empty like a small hole, not hole, like dip, a small dip is there. So you can put your sample there. And also if you observe, so in this you can do many sample at one time. So like you see, you can name like A1, A2, A3, and then also B1, B2, C1, C2. So in your instrument, in this multi instrument, uh, in your software where you are using your PC, there will be option. So which where is your sample? Okay, where is your sample? and you can just say, okay, A1 is my sample, and suppose C3 is my sample, B4 is my sample, and then it will just, uh, it will analyze those samples. So how it is happening, how analysis is happening. So you have some laser beam, okay? Laser beam is hitting on your, sample with this matrix, okay? And because this matrix is absorbing, this laser light, I will talk about that. And then what will happen? Because your this matrix, which is it will get fragment easily with this laser light, and then some of the sample molecule will get ionized, okay, and then they will start, they will be dissolved from this metal plate, okay, and then they will, because you have some, as we talk, like you see here, acceleration chamber is there, and then it will move to mass analyzer, okay. So that is the principle. So how it's working? So, okay, we use laser beam in MALDI. So, laser will provide energy to the matrix. Okay. So, what will happen by that? Desorption will happen. That means your molecule plus your molecules and your matrix, they will dissolve from this surface. Okay. And it will it will go in gaseous form. Okay. And also it will ionize. So, mainly proton transfer to analyte. I will talk about that. Okay. Okay, so you can use different kinds of, so it depends on your matrix. Okay, so there are variety of matrix based on, aromatic molecule you can buy. So I will talk about that also. You can buy them and you can use them for, uh, yeah, for this MALDI. So each those matrix molecule, they can absorb different light. So suppose if they are absorbing 337, or suppose if they are absorbing 355, or suppose they are absorbing this IR light, so you have to use corresponding laser. Okay, there are different variety of laser. You can just change this laser from here, and then it will just, yeah, analyze your sample. Okay, and then yeah, it will, your sample will again go to mass analyzer after ionization, and then it will go to detector, and then you will get this mass spectra. Okay. Okay, so yeah, so how to make this, sample if you want to make? So what you need to do is, whatever sample you are having, you dissolve your sample, okay, first of all, okay, and mostly dissolve in acetonitrile and water, or, as we know that mostly people use this polar type solvent, or you can use this one, okay, and you see we use even some acid, okay, so we can use some acid, and yeah, and concentration should be very low. So you don't need to have millimole concentration. You can go for, picomolar. Okay, so you can understand it's too less, right? It's very diluted, because uh, we don't want too much for, mass analysis. Okay, we don't need too much sample. Okay, so that's why. So you can have the matrix solution. How to make that matrix solution? You can, suppose we use this alpha cyano 4 hydroxycinnamic acid, okay, CSCA. You can just buy this from Sigma or TCI, okay, so it's very easy to, or also suppose you have 2,5 dihydroxybenzoic acid, okay, so you can dissolve them in some, because they are highly polar, okay, so you can dissolve them in acetonitrile water mixture and use some, acid. We are using some acid because this is very viscous, okay, so, and also this is very acidic, okay, so it will not be easily dissolved, okay, so that's why we need this trifluoroacetic acid, right? Okay, and then you just mix them, sample and matrix, we mix them, okay, it's up to you how you want to mix, but yeah, 1:1 you can consider, okay, so just mix them, and then you just spot on your target plate. Just this is the target plate, okay, so you just, so actually MALDI is very easy, okay, so you don't need to, it's very simple, it takes like 5 to 10 minutes and your sample will be done. Okay, so, okay, and after because there will be some solvent after you apply this sample and matrix, so you have to evaporate that. Okay, so you can just wait for some time. Okay, because these methanol and acetonitrile, they will evaporate very fast. And I think sometimes people use even some, put them in oven at 50 degree or 60 degree, even water will evaporate. And because they, when they evaporate, what will happen? uh, your, because your sample and matrix only remaining without solvent, they will start co-crystallize, okay, and when they co-crystallize, it's good, because it's like solvent and your matrix is together, okay, so If you use your laser to excite your molecule of matrix, your sample will easily ionized. Okay. Okay, so then what you need to do, just insert your plate, okay, and run the multit of this instrument, okay. So someone is Mariam is asking, do we need to hydrolyze the sample first, or can we use polymers directly? You can use polymer directly, okay. So you don't need to hydrolyze. It's possible to use the polymer, but suppose your polymer is not dissolving, then go for like malt. You can go for Maldi or what is that, field desorption method, okay, where you can just put your sample, solid sample directly, because if your polymer is not dissolving, then it will be difficult to use ESI, yeah, ESI and all, okay. Okay, so I talked about Maldi matrix. So there are variety of Maldi matrix, so you can use like for peptides and proteins. So you can use the CHCA, SA, DHB. And then for nucleic acid, there are popular one, HPA, DHB. So you can decide like whatever you want to, whatever your sample is, okay? And also for small molecules, you can use these kind of matrix, and these are available, okay? So commercially we can purchase them. And for like if we have ionic liquid matrix, okay, so you can use those also. And these days even graphene oxide nanomaterials are possible, okay? So there are variety of matrix available these days. So if you have sample, just try to do, okay. Okay, so there is another one. You have fab mass spectrometry, okay. So what happens in this, you have you will uh, what you will do, you will have some atom gun, okay, instead of like in Maldi we have some laser, right? So in this case you have some atom gun, so where you like suppose argon gas, okay, argon gas beam, okay, and you have suppose your sample, okay, so you can have solid sample also, just put it on the surface, and then you irradiate it with the atom gun, okay. So what will happen, because of that your molecule will leave the surface, and then it will ionize, and then yeah, it will move to your mass spectrometer, you can say mass analyzer, okay. So you see, your molecule will get the energy from this atom gun, because of some atoms are irradiating, and then your molecule will be ionized, okay. And why it is happening, so suppose we used a xenon atom gun, so first xenon atom will strike the matrix, so we have some matrix just like Maldi, okay. So for example glycerol, and it will cause yeah, sputtering of ionized molecules, okay. So your molecule will be just ionized, and it will just move, okay. So how it is happening? So you see, your xenon will convert to xenon, plus, and then it will again change to xenon neutral, and then it will hit on the glycerol. Okay, so some, yes, as I told, matrix will be there, and then that glycerol, it will transfer one proton to this molecule. Okay, so yeah, this is just as I talked in starting. So yeah, you may get some adduct or some simple plus one charge. Okay, plus one charge. Okay, so how this this atom gun, how it is working? That's very important to understand. So xenon gas will enter the atom gun. Okay, there will be some gas purging here. Okay, so and then this xenon, it will get ionized, okay. So you can use some filament, some electric filament, so your xenon will get ionized, okay, is Xe plus. And then what will happen, we will use some acceleration chamber, and then your xenon gas, xenon positive charge, yeah, xenon plus, it will accelerate by electric field, okay, and then it will gain a kinetic energy, right? And then it will hit on this xenon, this plus, it will hit on another xenon which is neutral, and then what will happen, kinetic energy will exchange between these two, and then this neutral xenon will become, it will gain kinetic energy, so that's why we are writing fast. And this one, this will be, what to say, yeah, it will become less kinetic energy, okay, so this xenon plus. And now we can use this xenon fast, okay, to go and hit on the surface, okay, surface, okay. So I hope you understand. So what is the result? Result is we are getting high energy neutral xenon beam, okay, out of the atom gun. So in atom gun, you cannot have, xenon with very high kinetic energy. So that's why people, when people talk about this atom gun, it's not just, xenon gas is there and you are just, attacking on the sample. No, it's not like that. So first, there will be some ionization and then acceleration and then charge exchange and then high energy neutral xenon beam will be created. Okay, so please understand this is very important. So if you see this atom gun and all, so you can understand what's happening inside. Okay, so okay, okay, so this is atmospheric pressure chemical ionization. So in this case, what's happening? So similarly, you have some liquid sample, it's going inside, okay, and then you have some heater, okay. So and then you have corona discharge. This is just, high electric field you have applied, okay, okay, so on some metal, and then your this liquid, it will get ionized and then it will move to analyzer, okay. So this is your, suppose nebulizer gas we are using, mostly people use nitrogen. So you are using nitrogen, what will happen? It will hit on this corona discharge and then it will get, ionized, okay. And then you will have some molecule, right, analyte. So what will happen? Overall this molecule will get ionized, okay. This is just the mechanism, so don't worry about this, just understand that your molecule will get ionized with the help of some, nebulizer gas, or even some moisture will be present there. So yeah, like whatever liquid we are using, so here maybe they have used water. So okay, so what is the, method? So first, you insert your liquid sample and then, you have some nebulized, means some, you are passing some nitrogen gas or argon gas, and then you are heating also, so vapor will be generated. And because of this corona discharge needle is just high potential, okay, very high potential, okay. So what will happen? It will ionize the solvent, or even here you have seen I am talking about nitrogen. Okay, so both of them is possible, and then finally proton transfer will happen. So what we talked here. Okay, so it is great for non-polar to moderately polar compounds. Okay, and this yeah, we can use different like LCMS, GCMS. These day people, yeah, use, because separation before using mass spectrometer, if your molecule is like having mixture, it's good to separate them first. Okay, okay. And similarly, you have atmospheric pressure chemical ionization. Okay, so same principle. Okay, just like a previous one, but in this case, what we are going to this 1 minute. Okay, yeah, this is same actually. Yeah, so just this is the scheme. So yeah, so your sample is going and then solvent is going and then there is a corona discharge, the very high potential, and then your analyte and solvent will be first get ionized, and then some of the analyte will get ionized and then they will move to vacuum. Okay. Okay, so we have yeah, APPI, which is yeah, similar like APCI. So in this case, what's happening? We are using some sample, and in this we are using some liquid which is light sensitive. Okay, so light sensitive. So because of this light, what will happen? Your sample and also your solvent, whatever it is, they will get ionized, okay, and then they will go to mass spectrometry. So all of them have like a similar concept, okay, all of them have similar concept. Okay, so what's happening? First you have sample and then you have UV lamp, okay, which will help in photoionization, and then in this case also ionization is happening in atmospheric pressure, okay, and then it will move to mass spectrometer. So this is good for non-polar analyte with low ionization energy. So this is also called soft ionization. Like this is not hard ionization. Okay. and often use some dopant like toluene, acetone, because they can absorb some light, okay, and then they can help in ionizing your sample, okay. So that is the reason. So another one is yeah. So all APCI, APEI, and this ASAP, right? So all are similar. So in this case, just they are putting the sample here itself. Okay. So you can just take your sample in glass tube, in solid sample itself, and you just purge your this nitrogen gas, and then your molecule will, this nitrogen gas will first get ionized because of this corona discharge, okay, and then some of your analyte will be, because nitrogen gas will hit on them, and they will get dissolved from surface, and then this analyte will get ionized, and then they will go to uh, mass analyzer. Okay, so similar concept. Okay, so now, okay, so if there is any question, please write in chat box. So Dipender is asking, 70 electron volt energy is used in ionization. So see, yeah, that's very important question. So 70 electron problem with 70 electron volt electron beam is that is too much energy, okay. So if you use that will destroy your molecule. Destroying means you will get lot of fragmentation, okay. So that is only used in EI method, okay. So electron impact ionization. So whatever we talked like ESI, MALD, and then we talked, APCI, APPI. So in these methods, we are not using, electron beam. We are using different method. Okay, so that's what I discussed. Okay. Is there any question? Please write. So you people have lot of questions. So if you have any question, please write. I will be happy to answer. Okay. So if there is no question, then we can move further. At least you can write that there is no question. So I know that you are there, right? Okay, no one is asking anything. Am I audible? Hello? Okay, okay. So let's move to mass analyzer. So, after you send your sample, you send your sample to, like you send your sample to mass analyzer. So it should happen only when your molecule is ionized. Okay. So after that, mass analyzer will start working. So as I have written here, so any ion after leaving ion source, okay, they will be separated according to their M by Z ratio. Okay, so in this area, mass analyzer area, ions are accelerated by both, it could be actually electrostatic and magnetic field also. Okay. So there are a variety of mass analyzer like quadrupole is very famous, and also TOF analyzer is very famous. And these days, yeah, we have Orbitrap analyzer, and this is ion cyclotron resonance analyzer. Which this is also called ICR. So ICR is very expensive. So I will talk about this also. And then you have Kingdon Trap. Okay, so let's move to quadrupole mass analyzer. So in quadrupole mass analyzer, by name itself, we can understand there is four, pole. Okay, just like dipole, you have quadrupole. Okay, so one, two, three, four. Okay, so if it is suppose hexapole, so that means you have six pole. Okay, and also these days there is a octapole. Okay, so that means eight pole is there. So in this case, what's happening? Your your molecule when it get ionized in this ionization chamber, and then it will move to your mass analyzer side, right? And then there we will detect them. Okay, not detect, but we will select which mass should go to detector. Okay, I will talk about that. So okay, so yeah, quadrupole consists of two pairs of parallel rod. Okay, and they are, so this quadrupole is having some DC and RF voltage. So RF voltage means radio frequency voltage. So that is for tuning. So sometimes it can be plus charge and sometimes it can be minus charge. Sometimes it could be neutral. So we can tune the charge on this pole. Okay, so it helps us in controlling what kind of molecular ions or fragment ion can go and pass to, can go to detector. Okay. Okay. So yeah, as I told, so ions are scanned by varying this DC and also RF quadrupole voltage. Okay. Okay, so what I mean in previous slide is you have suppose positive ion, okay, and you see, and you have some negatively charged pole. So what's going to happen? This positive charge ion will, like attracted to this negative charge pole. Okay. Now suppose you have two poles. Okay, and what you are doing here, you see, you have positive charge, and it is going. Okay, but you observe. So what we are doing by using this RF voltage, which is, we can use, we can alternating current, we can change their, mode, like sometimes it is positive mode, sometimes. So suppose at time t, at time, yeah, at t, at, yeah, maybe, right, at time t. So they have positive charge, and suppose at time T dash, they are having negative charge. So suppose you have some positive charge ion, okay, and it is going in this, in between these two poles. But so suppose it's coming here, so it will be repelled, right? Because this is positive charge. But when this positive charge it becomes negative, what will happen? It will be attracted, right? So when this charge is moving, we are controlling this positive and negative charge, positive and negative direction, like positive and negative polarity of these poles. Okay, so you can control the direction of, like this, how this charge ion will be moving inside. Okay. Okay, now similarly, so problem is if you use this one, you can only control the movement of your charge in two-dimensional, right? Because this is just two pole, right? So that's why people have, like scientists have discovered this, quadrupole, okay? Because our ions will be generated in three-dimensional space, right? So we cannot control them very nicely in the two-dimensional, pole, right? So and that's why there is a quadrupole, hexapole, octapole. Okay. So you can see when it is, you can control the movement of this. Okay. So I hope you understand what I'm trying to say. Okay. Now you see, you can have, different M by Z, right? As I told. So okay, different M by Z in the quadrupole. Okay, so you see some of them is even going outside. Okay, so you see this blue one is just going out of that. Okay, because there will be some interaction between these positive charge and negative charge. Okay, and because of different mass, some mass is very large, so they will just deflected more, and they will just get out of the, like they will hit on the surface. So what I want to say is, we may not analyze them if we have some particular, voltage that cannot, keep them inside that quadrupole. Okay. Okay. So yeah. So for example, here you have, ion source, and they are going inside. You see this red one is going to the detector, but this blue one is cannot go through the detector. Okay, so only red one is going. So what I want to say is, like, we can tune this voltage of this pole, and we can control which M by Z ions should go to detector. Okay. Okay. And now this is second example, right? So now you can control the charge of this quadrupole, and then you see blue one can go to the detector. Okay. Okay. So now what we need to do, you have ion source, and now suppose with time you are just tuning this voltage on this pole, and you see one by one you can get uh, all of the mass, okay, one by one. Okay, so this is how, yeah, quadrupole mass analyzer is working. Okay, so next is TOF mass analyzer. So what's happening in TOF mass analyzer? Suppose this is like, if suppose it was MALDI. So suppose you dissolve your molecule from surface, and then you have some acceleration chamber, right? And then your molecule, that ionized molecule, it is moving inside. Okay, so you have some free space. Okay, you in TOF, a time of flight mass analyzer, you have some free space. Okay, you have some free space, so where your molecule will ionized molecule will move inside. Okay, and now suppose at this point where your acceleration chamber was there, at this point they have gained some kinetic energy. Okay, so those molecules, they have gained some kinetic energy. Now because of those kinetic energy, they can move, right? But they are having different mass, right? So what will happen? uh, heavier ion, they will move slower. Okay, and a smaller molecule, they will move faster. Okay, I hope you understand what I am trying to say here. And then so what will happen? A smaller molecule will move fast, and then it will hit on the detector. Okay, later little bit larger molecule will come and hit on the detector, and like that it will work. Okay. Okay, yeah, yeah, I will talk. Actually, I have, yeah, something I have written also. So, okay. So in TOF, what's happening? You have some drift region. Okay, you have some drift region. So in that, what we are doing is we are measuring time. Okay, so we are measuring the how much time your ions are taking. Okay, how much time your ions are taking to travel from here to here. So as I told, heavier ions, they will move slower. Okay. Okay, Nisita is asking, as you mentioned, large molecules will deflect more. Yesterday, I'm not sure. Yesterday, I mentioned about POA. Yeah, yeah, yeah. If you can, ionized your even biomolecules with higher molecular weight, we can say, so if heavier molecule is there, they will be slower. Okay, and if a smaller biomolecule is there, they will move faster. Okay, so we can say same thing. Okay. And multitop is used for proteins and biomolecules, so same principle. Okay, same principle. So what's happening? It will measure ion travel time, and then it will determine the m by z. So I will show the equation actually. So it's very fast and sensitive. So you can understand. It can detect if your molecules in solution, or even in in this like method, like your molecule dissolved molecule. If it is just 5 femtomolar, you can see of peptides, for example, this method can detect them. Okay, so you can understand, is so important. So great for high mass biomolecules. And as in this case also, molecules are just leaving the surface at one time, and then depending on their fragmentation, they are just moving. So you can capture all of them in one time. Okay, so okay. So normally this kind of mass analyzer is used with MALDI. So you must have heard MALDI TOF, right? So because we are using MALDI for ionization, and we are using TOF for this mass analyzer. So that's how MALDI TOF is like invented. So because we are using resorption method, so even we can use for proteomics and biomolecular analysis. Okay, so what's happening in TOF? Ions will be accelerated, okay, through a flight tube. So as I told, you have some, suppose your sample is here, and then you used some, maybe suppose we are talking about laser, so we use some laser light, and then some sample is they will get ionized and they will leave the surface, and then you have some acceleration chamber. Okay, you have some acceleration chamber, you can say. Sometimes I get confused, so just okay, this would be maybe minus. Okay, and you will have some acceleration chamber, and there will be some small slit. Okay, and so there will be some small slit, so sample will go inside, and then after that you have this some drift region. Okay, drift region means there is no field, you understand, there is no electric field and magnetic field, so you just let your molecule move here freely. Okay, your molecule will just move, and then there will be detector will be there. Okay, so yeah, so this is also called flight tube, so it's just empty space. Okay, I hope you understand. And how much time your molecule or your ion, how much time your ion took from here to here, it can, if you know this time for your ion, it can tell you the what is the m by z for that. Okay, okay, so I hope you understand. Okay, yeah, so here you can understand better, I think. So your ions are there, you accelerated them, and once this is called flight tube. Okay, this is called flight tube. So your ions are moving, and I will talk about this. What is it? This is called reflectron. Okay, this is called reflectron. So, and then it will go to detector. Okay, so you see detector is there, and then it can tell you that, okay, what m by z ratio is arrived. Okay, okay, so how, I talked about, based on the how much time your ions are taking, so how we know the m by z. So you see here, uh, because here when your all the large molecular ion and small molecular ion here, they will have kinetic energy, right? Some kinetic energy. Okay, so this kinetic energy we can estimate how much it will be. So this will be just q into v. So this one, okay, q into v. Okay, and now we can estimate the velocity. So how much will be the velocity of these, molecule, these ions? Okay. So if you use this formula, so you can have a square root 2qv by m. Okay. And then if you know the velocity, if you know the velocity of each ion, you can estimate the time. Okay. Time will be just, we already know how much length is there, right? So length will be this one. This is L. So how much length is there? So L by V, right? And then you know this V already. So you know V here. So just put it here. Okay. So L by under a square root of 2qV by M. So you see this time is directly proportional to L. Okay. L and a square root of M by 2qV, right? So if you know this time, and you know this length, you can know what is the m by q. Okay, I hope you understand. Okay, so yeah, so that's the principle of this mass TOF mass analyzer. So based on how much time your ions are taking from moving from one from a starting point to this detector, that time then you can know how much m by z will be. Okay, 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 so you see here, yeah, this is the example. So here your sample is dissolved from the surface, and then it's moving. There is a kinetic energy they got, and then they are moving. Okay, and they in drift region, and then they come and they hit on the detector. So we know their path length, right? So that how much time they are taking and how much this length is. So we can know using this formula. We can know what is the m by q. Okay, and you see, you can have all of them because all different ions, they will move at different time, right? I hope you understand why they will move at different time, because heavier mass will, heavier mass will move slower. So if suppose m1 and m2, suppose mass is m1 is higher, so what will happen? Time this one takes t1 will be, is it, no, 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 so it should be, yeah. So if mass is higher, what will happen? It will take longer time, okay? And if mass is less, it will take lesser time. So you can just know, okay, this mass has detected, okay? Okay, now I was talking about what is this? So this is reflectron. So sometimes what happens? Sometimes what happens is when when these molecules are ions are moving and it's going to detector, then they may have some difference in kinetic energy, okay? So they can have difference in kinetic energy, so we use this kind of reflectron. So reflectron is like a, you can say charge mirror, okay? So what's happening, if you have heavier molecule, big one, they will have, velocity less, right? So they will not go more inside and they can just come outside easily, okay? And if you have this a small one can go deeply, okay? And then they will come, so they will take, what to say, what I want to say is the time taken by them, if there is a difference, this reflectron will help them in, like balancing them, okay? And then you will get better resolution, okay? So okay, that is the main principle, okay? Okay, so let's move to other mass analyzer. So I already talked in yesterday session, right? So charge in electric and magnetic field. So we already know if you have suppose positive charge and you have some magnetic field, what will happen? Your positive charge, if it is moving in this direction, they will be deflected. Okay, they will be deflected because of some magnetic field, and that deflection value, it will be also like equal to centripetal force, right? mv square by r, and then you can know how much deflection is there, right? R is equal to mv by qb. Okay, yesterday we talked this. Okay, similarly, if your moving charge is moving and you apply some, electric field, then what will happen? Your charge will be deflected. Okay, so you see in magnetic field and electric field, in both case, charge will be deflected. And you can know this, how much deflection is there using this formula. Okay. Okay, so this is very important. Okay, so please try to, yeah, focus here. So this is ion cyclotron resonance. This is also called ICR. So you see, I just here want to give you example. Suppose you have some charged particle. Okay, so Guru is asking, if we have two molecules of similar mass, how do they travel and is it possible to identify in TOF? So you see, if you have uh, and don't say similar mass, okay? Similar mass is, yeah, it, as I talked yesterday, we should not say similar mass. If you have same chemical formula, okay, and suppose maybe we can, best way to say is like if you have isomer, then yeah, it will be difficult to just distinguish them by, this mass analyzer, okay? So maybe first you should do, like go for, like use some separation method like LCMS, LC, or liquid chromatography, or GC you can use. Also there are other method that I will talk about, and then maybe you can separate them. So it should have some difference, molecular formula or molecular, yeah, there should be some difference, okay? Then only, yeah, this kind of, mass analyzer can detect them, okay? Otherwise you should go for, first go for purification and then only, and like put your sample inside this mass spectrometry, okay? Okay, so in ICR, suppose here I am showing this charged particle and we have some plate, okay? Some, you can say, some electrode, okay? And now suppose, okay, yeah, you see, when your this charged particle is moving, what's going to happen? Okay, what do you think will happen? So when suppose this charged particle is moving and suppose it comes nearby here, okay, so if it comes nearby here, then this electrode, it will generate some electron, okay? It will means it will just pull some electron, okay? So if suppose you have some circuit, okay, and then some electron will be pulled towards this, okay. So this is called image current, okay. So if you don't know about image current, please, I think we read about, AD current and also please go through that. So if you have some positive charge, yeah, it's coming nearby this plate electrode, then because of this positive charge, some electron will be coming near, electron will be coming on this plate, okay. So because of some movement of electron, what will happen? You will see some voltage, okay. If you suppose use some voltmeter, you will see some voltage, okay. Okay, that is called image current, okay. Now this is another example. Now when your this positive charge, it is coming nearby this, okay, coming nearby that. Okay, so there will be similarly. So sometimes when this charge is going towards here, you will get some image current here. And sometimes when this charge is coming on, this right plate, right electrode, then you will get some positive this image current here. Okay. So what will happen? Sometimes this will be negative, positive, and sometimes this will be positive and negative. Okay. Okay, and also this charge particle, if it is moving, okay, in a, like circular motion, then you can use this, as yeah, we already talked in magnetic field what will be the value. So you see, if you have, that BeV is equal to mv square by r, right? So we can have V by R is equal to, yeah, BE by M, right? And now you see this V by R is what? That will tell you the frequency, okay? That will tell you the frequency of this movement, okay? This cycle, okay? So when charge is moving, so you can know this, how much is the frequency of this movement, okay? Like how many cycle it is moving in per 1 second, okay? Okay, and now I want to tell you, if you know this frequency of movement, okay, if you know this frequency of movement, you see this is related to mass, and also it is related to this E, right? So you can correlate. So if you know this frequency, you can know your mass by charge ratio, okay. Just like, as I talked in this TOF, right, TOF, you see that in TOF also time of flight is correlated with mass of your charge ion, right? So similarly here also you see frequency of this movement of your charge particle is correlated with their mass by charge ratio, okay. So this is very important if you want to understand ICR, okay. Okay, so here I have shown you example. Yeah, it is similar, but I want to show you that you have suppose very large mass is more here. Okay, so they will generate higher current, right? They will generate higher current, and also their frequency will be correlated with this equation. Okay. And also here, if charge particle is size is very low, like mass is less, then also you will this omega, this frequency will be less. That means it will move slowly, okay. And no, actually this will move faster, okay, and this will move slowly, okay, because omega is correlated inversely, right? So okay, okay, that's what I am trying to say. Okay, so here I want to say, in theory, this rotation should be constant. Okay, it should be consistent. It should not stop. It should just move on, because you are applying magnetic, like electric. What to say? You are already applying magnetic field, so it should rotation should be having some frequency, and that should be constant. So you see, this is just a constant. Okay. So because of frequency, it's moving at a constant frequency. So image current that is generated, it should be constant, right? So you should get this kind of image current. Okay. Okay. But in reality, what happens? You don't get like this. Okay. You get actually like this. Okay. It's like decaying. So why it is decaying? Because you don't have only one charged ion inside. There are many charged ion, right? So we are not just, in mass analyzer, uh, from ion source, right? So ion source is not just sending one molecule or one, you can say one molecular ion. Okay, it is sending many, right? So if lot of molecular ion is going inside, so there is a chance that they may hit each other, right? So because of that, their image current is also decaying with time. I hope you understand. Okay, and you can use Fourier transformation. Okay, you can use the Fourier transformation, and you can change this to the spectra. Okay, you can change just like NMR. Okay, and you can get what M by Z was which one. Okay, I hope you understand. This is very important in ICR. Okay, so now I want to talk about, yeah, this is actually a very old method, but yeah, it's good to know. So this is a Kingdon trap. So in this case, what you have some cylindrical electrode, okay, and you apply some negative voltage, okay, negative potential. And suppose you have some mass, different mass molecular ion, okay, and they will circulate around this cylindrical electrode depending upon what is their mass, what is their mass, okay. Okay, so yeah, they will just circulate and move left to right. So here I want to show you some example. So this experiment is done in zero gravity. Okay, so this what I am showing here is actually consider is needle. Okay, and what I am showing this movement, consider some water droplet. Okay, so let's see. Okay. So it's just telling that how if you have some charge particle, how they will move. So this is the done in the, yeah, zero gravity. So this is just the kind of consider some needle, okay, knitting needle, okay, and he rubbed with clothes, right? That means after you rub with the cloth, what's going to happen? It will get charged. You see your water molecule, water particle, it's moving just like this, okay. So I'm showing this because sometimes when we look at this kind of picture, cylindrical electrode and there is a charged particle, we may not visualize how it is moving. So you can understand that, okay, such a interaction is possible. Okay. Okay. So there is another one, Orbitrop. It's, you can say it's almost not similar, but yeah, like Kingdon trap. So in this what's happening? You have two electrode, okay, two electrode, okay. Uh, so in this case also your molecule, so suppose your molecular ion, molecular ion, suppose M1 plus, M2 plus, they are going inside, okay, they are going inside, okay. I think from here, okay, they are going inside and they will move inside, okay, they will rotate, okay, with some frequency omega, okay. And when they are rotating, we can relate this with mass, right? We can relate this with mass, and we can know what was the M by Z ratio, okay, for that molecule. Okay, so frequency of such a rotation, that circulation, it will be related with M by Z, as I already told. Okay, so FZ is axial frequency. So this, because this is axial, right, axial frequency, and K is just constant. So yeah, that depends on electric field strength. So electric field means how much potential you have applied, okay, on these two. And so you can know the M by Z. So in all of them, concept is similar, right? So you should know the correlation between, like if it is a circulation, circular motion, or like kind of any rotation. So we should know the frequency, and then we can correlate with the M by Z, and then we can know how much M by Z is there for some molecular ion peak or fragment ion peak. Okay, so image current will be generated by the axial motion, okay, which will be detected on outer. So this is outer electrode, okay. Okay, so as I told in FTICR also, there is a signal is time domain transient, so which contains all frequency of the ion. So it will be like maybe something like this. So not only one, okay, there will be many, right? So not only one ions are there, there will be many ions, okay, and we can transform this, this using Fourier transform FT, and we can get some mass spectra just like NMR. Okay, so you can get some mass, and they will be having different m by z. Okay, different m by z. Okay. Okay, so you will, so yes, one thing I would like to highlight here, you see, in this case, you can just know the frequency and you can know what is the m by z. So, it, so this is working as a detector also. Okay, so it is acting as a detector. Okay, so you can just know m by z directly. So you don't need other, so in ICR and this Orbitrap, you don't need external detector. Okay, so you can just use this as a like mass analyzer as a detector. Okay. Okay, so here I have made the, yeah, like difference between them. So in Kingdon trap, yeah, ions are trapped in a cylindrical electrostatic field. Okay, so there is no magnetic field, and also use electric fields to trap and analyze ions. Okay, and as I told that in a so that experiment in zero gravity, ions move in a spiral orbital. Okay, between central wire, that is electrode, and outer electrode, and then ions are ejected based on this m by z and detected externally. That is Kingdon trap. Okay, so indirect m by z measurement via ion injection. So another one is orbit trap. So in orbit trap there is a difference. So ion will oscillate around a central electrode in electrostatic field, and it will have very high resolution. Okay, because it's very sensitive. Okay, so no magnetic field is applied, and also oscillation frequency we can directly know what is the m by z, and also it will detect the, we can know the m by z measurement without any detector. Like, so here itself we can detect what is the m by z, so you don't need external detector in this case. Okay. Okay, so let's compare these three, Orbitrap, FTICR, and quadrupole ion trap. So you see, field type is in Orbitrap, it is electrostatic. In ICR, mostly it is magnetic, but yeah, you can also use electrostatic. And quadrupole, as I told, you need some, RF electric field, because we want to, change the polarity of those quadrupole. And in the Orbitrap, yeah, it is axial oscillation. Okay, and in ICR, name itself suggests, so it is having cyclotron motion. And in quadrupole you have resonance in 3D RF field. Okay, so it's just yeah, it's different. Okay, so what is the detection? So in Orbitrap and FTICR, both are producing image current. Okay, but in the quadrupole, ion will be ejected and it will move to detector. Okay, so yeah, here you can see resolution for different instruments. So you can see this FTICR is, yeah, best instrument till now. Okay, FTI, it can have a resolution of 500,000. Okay, so it's too high. 1 minute. Okay. So yeah, best if you want to really, do mass analysis with very high resolution, yeah, go for FTICR. But I think not so many FTICR is worldwide available. Okay, so it's very expensive. Okay, so magnetic field. So we apply in FTICR, we are applying magnetic field. Okay. And yeah, so you can see you can use Orbitrap for proteomics and metabolomics, and for ICR you can use high-end research, yeah, very sophisticated. And for quadrupole, people use it for some bench instrument, like it is vastly available. Okay, in lab. Okay, so let's move to a mass detector. So there are, I think, 3 or 4 famous ones. So let's go each one of them. So there is a Friday Cup detector. So what's happening? So you have some ion beams, okay, and there is some kind of shape. Actually, Faraday cup is just there is a shape which is having some cup type shape, and your this ion beam will hit on the surface. Okay, so suppose you have M plus and it hit on the surface, what's going to happen? It will this molecular ion will be neutralized, right? So if M plus want to neutralize, what will happen? One electron will be ejected, right? So if suppose this surface is there, M plus is coming and hitting, what will happen? One electron will go, right? One electron will go from this I think we can say electrode, right? Okay, and that loss of electron will, what will happen? Because of that loss of electron, there will be generation of electric current, right? And then we will amplify that. Okay, how much current, how many molecular ion peak has hit on them? Okay, and then it will be amplified, and then you will get the signal. Okay, so that will go to like amplified, and then you will get the signal. Okay, so here I have shown in more, yeah, better way. So you have some metal box, this Friday cup. Okay, you have metal box and ions is coming inside, and then it is hitting on the surface. So what's happening? You see, you have positive ion, suppose, and this is because the metal, there will be lot of electron, right? So what will happen? One electron is moved, neutralize this positive ion, and then this because one electron is moving, right? So there will be some generation of current. Okay. Okay. So what is the principle? First of all, ion will hit the inner surface, and then charge will induce current. Okay. Signal will be amplified, and then data will be recorded. Just a simple process. Okay. Okay, so this is, though sensitivity is not so high, because it is what to say, we are not using much amplification. I will talk what I mean by amplification. So it is, though it is robust and reliable, but it is very less sensitive with respect to electron multiplier. And also in old mass spectrometer, people use this widely, but I think these days maybe it is not so famous. Okay, so let's go to electron. Let's move to this, discrete electron multiplier. So you see, in this case, what's happening? Your ions, suppose moving to the some metal box, okay, and you have some dynode. Okay, this is called dynode. Okay, you have some dynode. Okay, and these ions, when it will hit on the surface, okay, there will be some generation of electron. Okay, electron will be coming out. Okay, electron will be coming out. Okay, and because these ions, they are having very high kinetic energy, right? And they are coming and then just hitting on the surface. So this generated electron, they will have kinetic energy, and they will just move from, they will come out, and they will again go and hit on some surface. Okay, another side of surface. And now, because potential of this, suppose this is plus. Okay, this is plus, and we can say, okay, this is plus, and suppose this is plus plus, and this is plus plus plus, this is plus 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 plus. So I just want to say higher potential. Okay, like this is suppose 10 voltage, this is 20, maybe this is 30, this is 40 voltage, and maybe here 50 voltage. Kind of you can see here, like they have given 2000 volt. So it's too high. So what's happening? So when your electron is ejected and then it moves, and then more number of electron will be ejected. Okay, and then again it is going to move here, and because they are having high potential, again more number of electrons will be generated, and then again it will go here, more high potential. So kinetic energy of your electron will be very high, and then again it will hit on the surface, more number of electron will be generated. So you see, it is like a avalanche of electrons, right? Lot of electrons will be generated. So in this case, amplification of your signal will happen. Okay, because lot of electrons are coming, and then it will go to the where you can detect this lot of electron. Okay, so okay, so as I told, this is dynode. Okay, so what dynode does? Dynode will multiply your electrons. Okay, and it is used in electron multiplier, photo multiplier tubes, and also it will enable detection of very low ion signal. So even though here you have very low, like less number of ions which is coming and hitting on the surface, using this method, okay, using this method, you can get a lot of electron, coming out. So which will give you a lot high signal, okay, like very, what to say, signal will be amplified. Okay, so why it happens actually? So see, whatever material we use in this diode, it can easily release the secondary electron. Okay, so ion will hit the diode and then electron will be eject. Okay, and because of this cascade amplification through diode chain, because they are having different potential, right? So more and more number of electron will be generated. So yeah, so that is the concept. And also concept of this is similar to Friday cup. Okay, here what you see, but there is no amplification in Friday cup. Okay, so we are using some diode chain and then there is amplification. So that's why it is having much higher sensitivity. Okay. Okay, here I have given the example. So you can see in starting you have some metal ions and it hits on this one surface. Okay, one surface, and then because different surface is having different potential, more number of electrons are generated. So you may ask why? Because whenever you apply higher potential, so what's going to happen, more number of electron will be generated, because whatever electron is hitting on the surface, they are having more kinetic energy. So more kinetic energy means more number of electron is going to be released each time. Okay, so there is another one, photomultiplier detector. So in photomultiplier detector, actually it is also similar, but in this case, you this molecular ion, they are just hitting on this, some plate, and some electron is released. Okay, and this electron will hit on this scintillator. Scintillator is like some plate which will, when you hit with some electron, and then it will release some light. Okay, and this light will be detected by this photomultiplier tube. Okay. Okay, so beams are hitting on diode. Okay, and then secondary electron is released. Okay, and then electron hits a phosphorescent screen, this one, and then photons are emitted. Okay, and then photons will be detected by this photomultiplier tube. Okay, and that will be converted to electrical signal. Okay. So in this case, you see, if your detector suppose is here, this molecular ion is not hitting on them. So we can say that it is, better, because your detector will be more, what to say, like not damaged. Okay. So in electron multiplier, maybe detector may, that, surface of diode may get damaged. Okay. But in this case, it is not possible. So, okay, what is the advantage? It can detect low ion currents, and also it is resistant to direct ion damage and excellent for single ion events. So when you should use this, so yeah, you can use it because it is high sensitivity, and also it is longer lifespan. As I told, molecular ion is not hitting directly on the detector. Okay, so that's why it is having longer lifespan. And then also it is useful in, yeah, various kind of mass spectrometry. Okay, so here is the summary. So yeah, in photomultiplier tube, it is detecting your ions indirectly via photons. Okay, and also it is having higher durability and sensitivity, and also it is ideal. It is ideal for long term and low signal mass application. Okay. Okay, so there is another one, microchannel plate detector. So actually, it is also similar concept, but instead of having just one channel, in this case, you have lot of, like channel. Okay, and in each of those channel, you have this uh, dynode type of structure. So what's happening in each of channel, lot of electron will be generated. Okay, lot of electron will be generated, and then so what I want to say is, more signal you are going to get, because amplification of signal will be very large. Okay, so in MCP, and this is the shape of this. So okay. Okay, so this is just a thin plate with millions of tiny angle channels. Okay, ion will strike the plate and then release electron. Electron will, as I discussed previously, so it will multiply the signal. So it is high sensitive and fast timing, and yeah, it is used in various kind of mass spectrometry. Okay, similar concept that I talked. So you can see molecular ion. So molecular ion is hitting on the plate, and then it is going to this scintillator, and then uh, it is going to photomultiplier tube. So I talked about this in previous slide. So but here there are many. Okay, so lot of channel is there. So that is the difference. Okay, so that's why we call it micro channel plate. Okay. Okay, so I want to talk how I think this I can skip as I already discussed. So yeah, so I already discussed this. So electron is hitting on the surface, and because of different potential, they will, like you can amplify number of electron, and then you will get the better signal. So there are two types. So one is discrete dynode. So each plate is separate, and there is also continuous dynode. So it's like just a potential difference here and here is different, and they are like continue. Okay, continuous shape. Okay, so I think I can skip this as I already talked. Okay, so we may think, what is this diode made of? So, diodes are made of some metal or metal coated material, okay, which have a high secondary electron emission coefficient. So, why these materials we need? So they will give the high secondary electron yield and electrical conductivity and thermal and chemical stability, and also durability over many ions, because in mass analyze this mass spectrometry, lot of ions are hitting on your detector. So you want something which can your detector will not damage. So you want such kind of material. So what kind of material people use? So you can use beryllium oxide, magnesium oxide, aluminum oxide. Yeah, variety of them is there. And why it is used? So yeah, like this beryllium oxide, you have high electron emission and thermal stability. So you don't need to worry about these things, because whenever you buy mass spectrometer, yeah, these things will be there. But it is good to know these, how, what is the principle behind like working of these mass spectrometry. Okay. So sometimes I felt that there is a misunderstanding. So I want to highlight. So detectors will not determine M by Z. Okay. So detector is not telling you what is the M by Z. So you have to understand that. Okay. They only detect ions arriving and measure. What they measure? They measure when ions arrive. Okay, timing and how many ions arrive. So detector is just telling you about this intensity. Okay, intensity of peak. Okay, they are not telling you M by Z. Okay, M by Z is told by that mass analyzer. Okay, mass analyzer. Okay, mass analyzer will tell you what is the M by Z, and when it arrives in detector, it will tell you the what is the intensity. Okay, so I hope you understand. Okay, so common misunderstanding is, since all ions release electron, how does the detectors know their mass? So detector identify mass, it is wrong. Okay, so correct is detector only records impact. Okay, mass analyzer will yeah already sort the ions by M by Z. So you need mass analyzer. Okay. So yeah, I have again here shown. So ion source will ionize, mass analyzer will sort ions by mass by charge ratio, and detector will measure arrival and intensity of ions. Okay, so please keep this in yeah clearly, so that yeah, if you future you work in with different mass spectrometer, you know these things, right? So it will be helpful. So yeah, here is the analogy. So mass analyzer is like a coin sorter, and detector is like a tray catching them. Okay. So you know the type of coin by when it is landing, not just by hearing it hit. Okay. Okay, so this is the difference between electron multiplier and photo multiplier tube. So yeah, I think I already told about this electron multiplier, and in photo multiplier, just ions are hitting, and then there is a photo cathode, and then that because of that electron will be again generate, and again diode will be there. So you can say that in PMT already EM is there. Okay, but point is, in a PMT first light is generated. Okay, in PMT first light is generated. Okay, that is the only difference. Okay. Okay, so Now let's move to other topic, types of mass spectrometers. Okay. Okay, so there are variety of different instruments. So for example, here I have shown this LCMS. So what I want to say is that, see, sometimes when you have some sample and sample has suppose mixture, okay, and you want to analyze. So if you put them directly in the mass spectrometer, what's going to happen? You may get mixture of spectra. Okay, so it is difficult to find that what is the correct molecular formula. Okay, so if you have suppose different sample like A, B and C, okay, different sample. So first you separate them, okay, using you can use liquid chromatography, or you can also use GC, and there are other also. So in this what's happening is just that you have HPLC column, and then your solvent is passing through that column, and then your molecule will be generated due to different polarity, and uh, then they will move to we can control which one is moving, and we can move them to the mass spectrometer, and then we can detect them. So you see, with different time you can get different peak, different mass spectra, right? So because this yeah, this HPLC column, it can separate, and each analyte will arrive at different time, right? So it's very small, this axis, but what I want to say is that at time t1, suppose you got one mass spectra. At time t2, you got some other mass spectra, suppose. So you can get this at t1, what molecule came, you can know, okay, that maybe maybe suppose molecular ion peak was 50, and then in T2, suppose molecular ion peak was 60. So you know that, okay, this 61 is here and this 51 is here. I hope you understand what is the purpose of LCMS. Okay, so sometimes in LCMS, what will happen is that your okay, someone is asking me. Sometimes we have different MP with different pH as basic or acidic. Why and when? And we need to use different UV, AB, or C. I don't understand your question actually. So what you mean UV? Different. Please write your question again. I like try to say something, yeah, more clearly so that I can understand better. Okay, so yeah, maybe after I finish I can answer your question. Okay, so please wait. So in LCMS, as we know, in HPLC you have retention times. Okay, so like when some molecule is moving in column, okay, so this RT can shift. So suppose you run your so you run your sample, okay, at time t1 you got some peak, and then suppose at time t2 you got some other peak, okay. Okay, but sometimes what happens, this peak, maybe these two peaks were similar, okay, but they have shifted, okay, they have shifted because they came at t1 also and t2 also. So they have shifted, so we should do the peak alignment, okay. So we don't need to do manually, there are software that what I have shown here. So we have to do some alignment, okay, peak alignment, okay. So okay, so we can use this, match picking by M by Z, and also retention time. Okay, so it will help you in getting better resolution for your molecule. Okay, so yeah, so peak alignment, I just wanted to tell, in if you use LCMS, you may get some, peak alignment difference. Okay, so you have to use some software, and you have to align them and then analyze. Okay. Okay, similarly, you have this GCMS, right? So GC is a gas chromatography. So in GC, instead of passing the liquid, we are passing a gas, okay, and then you insert your sample here, okay, and this is your GC column. So in this column, your sample is moving, and also you are purging with gas. So this gas will help to move your this your sample inside, okay, and there will be some, what to say, some viscous you can say a stationary phase that will help, because of different polarity, that will help in moving your molecule different, analyte, yeah, molecule, we can say molecule differently, and then you can put it in your mass spectrometer, and then you can analyze them, okay. Yeah. So I want to say that GC is good for a small molecule. Okay, you should not do it for polymer and all, because they will not they will not move inside. Okay, because yeah, it will be very difficult to move them. Okay, so you can mostly use for a small molecule. Okay, which has a low, like low boiling point. Okay. So one of the thing you will see, people also analyze polymer. Okay. So how they analyze polymer? If you want to analyze polymer by GC, what you need to do? You need to first burn them. Burning means just heat them by to 400 to 800. Suppose you have P3HT. Sorry, you have suppose P3HT. Okay. So if I'm not wrong, P3HT has this structure, right? Okay, maybe C6 is there. C6 is there. C6. Okay, something, and of course, this sulfur and this sulfur will be up, but we don't need to mind that. Sorry. Okay, so what I want to say, any polymer, they have this, like, like they are having similar unit, right? So suppose, maybe like something like they have similar unit, right? So maybe like thiophene, maybe we can say. So we have to first do pyrolysis, like do 400 to 800. What will happen? This will change to the single unit, like monomer. Okay, so you will get monomer single unit. Now this is a small molecule, so you can pass them to the GC, and then you can know what is the molecular weight, if it goes to mass spectrometer, and you can know. So you using this method, you can estimate what was the molecular weight of your unit. Okay, so I just wanted to highlight that. Okay, so GC may MS, for if you want to do for polymer, you should first do the pyrolysis. Okay, and GC will help in separating and also identifying thermal fragments. Okay, so it can be used for identify polymer type, and also it can also tell you the degradation product. For example, you have P3HT, then you may get thiophene, okay? And also it can tell you the additive. Additive means sometimes when you synthesize polymer, then you have some, like maybe for example, you did synthesis Suzuki coupling, and you may have palladium catalyst, and in your polymer palladium catalyst is present. And if you want to make sure how much is present, you can do this GCMS in polymer pyrolysis, and you can analyze. You may get some peak for in mass spectrometer, you can get an additive peaks for your sample, and then you will know that, oh, that your molecule is, yeah, it was not pure. So best thing is you can do it for monomer, oligomer, and also characteristics, small molecule. Okay. But please understand, GC you cannot use for polymers. Okay. So if you just say GC, don't you cannot use directly for polymer. Okay. How you can use? You have to have some setup where you can use kind of oven, and where your this polymers, they should be broken down to a smaller unit. Okay, a small unit like monomer maybe, and then only you should pass to this GC. Okay, like this GC column. Okay, because otherwise what will happen, if you used polymer will go and just stuck there, so you should never use. There will be already, I think, here in this system itself there will be some oven, and it will be connected here. Okay, and you drop your sample here, and then it will be pyrolysis will happen, and they will be broken down, and then your samples would be induced inside. Okay. Okay, so GCMS is good for low, a small molecule. Okay, so for example, here I want to show you. So you see here you have OH, all are OH, right? So yeah, this is for water. So you see, water can have different isotopes, right? So here is 16 oxygen, 1H, and then also you can have deuterium. Here you can have 18 oxygen, and here you can have oxygen 16, we should say, oxygen 16. Okay. So if you use this GCMS, you can separate, first you can separate them, okay, by using GC, and then you send them to mass spectrometer, and you can get this, mass spectra, okay. So this is just for water, okay. Okay, so also, yeah, as I told, if you have some sample and you want to study the, water molecule, then, you can just pass that sample, and it has oxygen and this hydrogen, and you can get mass spectra, and you will get this one, okay? So similar thing we can do for oxygen also, okay? So sometimes people in photocatalysis, they use, such kind of method. So what they will do, suppose you have some, uh, suppose you did some reaction and you got some oxygen, and plus you have some sample. Okay. So first you use this GC method. Okay. You pass them, and then after that, yeah, this GC is connected with the mass spectrometry, and then your sample will go there, and then you can get the, whether oxygen is there or not. So if oxygen 16, oxygen 18, you can get this peak. And also I would like to highlight, sometimes in photocatalysis study, people use, instead of this O2, they can use 18 O2, okay? You can use this 18 O2 also, okay? So what will happen if this, suppose this 18 O2 was reacting, then you may not, what to say, if suppose it was what to say, it was doing reaction with your analyte or molecule, then this may be less, and then you can detect in your mass spectra that, oh, it is getting decreased. So that is one method to know, such kind of reaction, it is happening or not. So you can use the mass spectrometry. Okay. Yeah, that is called actually isotope labeling. Okay, so people use it. Okay, and then identify product fragments by mass shifts from isotopes. And then we can confirm the reaction pathways, and also, for active species. Okay, this is just a compare. So in GCMS, you should know that you can use it for volatile and thermally stable compound. And for LCMS, non-volatile, thermally unstable compound also you can use. And in mobile phase is in GCMS, it is inert gas, and in LCMS, it is liquid solvent. And column is, yeah, you already saw in GCMS, you have thin capillary, okay, with a stationary phase coating. But in LCMS, it is just a normal column packed with solid particles, okay, which is a stationary phase. And there are various kind of, stationary phase is present. So how is separation happens? So based on volatility and boiling point in the GCMS case, and in LCMS case, it is based on polarity, okay, size and charge. And often in ionization method is in GCMS, often people use electron ionization. So yes, so yeah, here in GCMS, because we want to fragment the polymer and all, okay, so we don't mind using electron ionization, okay, but in this case LCMS, you will prefer to use electro spray ionization, because this may be, you can use it for large biomolecule also. Okay, so you use often electro spray ionization. It's like just a sign, together with LCMS. Okay. Okay, so what is the use? So you can use both of them for a small organic gas, polymers, environmental sample. But please understand, in GCMS, if you want to use a polymer, you should first break them. Okay, make them a smaller monomer. Yeah, it's just a monomer unit. Okay, so there is these day, yeah, this SFC, MS is getting famous. So this is why, yeah, this is used for, analysis of, food products and all. So what is SFC MS? It is just, superfluid critical mass spectrometry. Okay, so you see this SFC-MS in starting, it started being popular 1962, but these day, yeah, it is you see first advanced SFC instrument is generated, and previously people just used for non-polar compound, but you see now people can use for, yes, all kind of non-polar compound, chiral compound, moderately polar compound, polar compound. Now you must be wondering what is it actually. So let's see. So superfluid critical mass spectrometry is, see, in the simple LCMS and GCMS, we are using some kind of, like gas or liquid as a stationary phase. But in this SFC MS, you can use the CO2, okay? CO2. And we want to, so you must be knowing this, right? So when you have this temperature higher than one particular point, and you have this pressure but more than some particular point, where your liquid and gas, they will act like as both, okay? So here it is only gas and here it is only liquid. But if you go to this supercritical temperature and pressure, what will happen? Your CO2, which will act like a liquid and gas also. Okay. So what is the benefit? Benefit of this is fast separation, high resolution, and it is green. So why it is green? Because, uh, in GCMS and LCMS, you are using some kind of, maybe liquid and some kind of, mm, in LCMS, we can say you are using some kind of liquids, which is organic solvent. So it is not good. But in this case, you are just using carbon dioxide. So though carbon dioxide is not good for, environment, but still, it's acceptable to use in a small amount. So it is good for chiral and non-polar compound, and it can be easily coupled with MS. Just problem, one thing I would like to highlight, handling with carbon dioxide at very, high pressure and high temperature, it's not good, right? Because you know that CO2 is just a gas, right, at room temperature. So at room temperature we want to use CO2, so it's like pressurized one. So it's actually, people, you can use it, it is safe, but yeah, it's if you want to do at large scale, it is not so good. Okay, so this is the configuration. So you have the carbon dioxide cylinder and you have this SFC model. SFC is just superfluid critical, okay? Supercritical fluid, okay? So you have, yeah, CO2 gas will go and then it will go to pump and then your sample will be here. So, just like a mobile phase. So CO2 will go and then your sample will move, okay? And then, yeah, it will go to your mass spectrometer also, okay? And then in mass spectrometer, your sample will be like what, your sample will be analyzed, okay? So, okay, that is the SFCMS. But you don't need to worry about this because, yeah, it's not, it's not so famous, okay? It's not so famous. It's getting momentum, like people are trying, but it's not, it must be very expensive also. Okay, so yeah, this one I already talked, right? Multi-top image. So it just multi is combined with TOF, which is, yeah, yeah, you need sample, okay? So without sample, we cannot do. So you need sample, okay? So you need to put the sample in sampler, and then, it's just like a LCMS, okay? But instead of liquid, we are using CO2, this supercritical CO2. Okay, so in a multi-top MS, I already talked, right? So laser is there and it hit on the plate and then ions will be ionized and then it will move to flight tube where there are no, field is there. And then you will get, in detector is there and then you will get some mass spectra, okay? Okay, so this is the structure. So you see it's very simple, right? It's very simple, and you don't need any curvy, this mass analyzer. It is just a straight line, so it's very good. And I already told why, how you can estimate this mass by charge ratio depending upon this time of flight and length of this flight tube. Okay, okay, okay. This is just the, I think if someone didn't understand, so this is your simple. So you have your sample, right? And then ions will be moving. So you'll see this is accelerated chamber. So now ions are moving, and this is called reflectron. Okay, and then ions will be separated. So different ions are moving. Okay, so now you see red one will go first. Okay, okay, that is yellow one, and then red one, green one, and then it is blue one. Okay, that is the mass TOF multi-TOF. Brooker is a company name, right? Someone is asking what does Brooker mean? Brooker is just a company name. Brooker has lot of, they are good in, yeah, developing, like NMR is there, then they are also making this mass spectrometer also. So Brooker is just a company. Okay, so lot of questions are there. 1 minute. Mhm. Okay, so let's answer one by one. So, okay, so see, someone is asking about Xenotrap in TOF. So Xenotrap is just, I will talk about that, I think, in later slide about, QTOF. So quadrupole TOF. So Xeno is just like it will help in, synchronize the movement of these ions. Okay, so it will adjust the, kinetic energy of ions, so that you will get better resolution. So what xenotrap does is like it will hold the ion, trap the ion, and then it can release after some time. Okay, so yeah, so it's I will talk about the quadrupole TOF, so then it will be clear. Okay, then another question is by Sneha. Yes. after flight tube if we are detector not reflection. Okay, so some see Sneha is asking what will happen if we don't have reflectron. So in old TOF you don't have reflectron, so you don't have good what to say resolution. Okay, so if you use the reflectron, it will help in adjust the kinetic energy of similar molecular ion, and then you can get better resolution. Okay, better resolution. Okay. Then that the Ratu is asking me why matrix is needed. See, as I told, in a in your in multi, for example, you need you need some matrix because we want to use some laser. Okay, so laser has some particular energy, and that energy can be used by these matrix. Okay, so your matrix molecule can be excited by that laser light. Okay, so that's why you need a matrix. So because we have, suppose you have some protein, you are not sure what kind of laser you want to use, right? So if you can mix with some matrix, and that matrix can get excited and get ionized first, and then that matrix can help you in ionize your protein or some biomolecule, then it becomes easy, right? Okay, if any other question, please let me know. Okay. Okay, so here I want to, so you must have seen, I think most of you must have seen NMR, right? So NMR instrument is very big, right? So we always think, yeah, and also it's very expensive. But look at this FTICR MS. So before seeing this FTICR, I never, yeah, imagined that mass spectrometry can be this much big, right? Because mass spectrometry is like a benchtop, right? Very small size, right? Like HRMS, FABMS also, Malditov, you see, it is not so big, right? But you see FTICR, it is so big, right? So why it is so big? So the best reason is in FTICR, we are using magnetic field, very high magnetic field. So someone is asking in this workshop, will I be cover the processing the data in LCMS and GCMS? No, 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 no. In this workshop, we are mostly, going through theory. Maybe in future, I plan to, yeah, do the processing of the data of LCMS and GCMS, because I think I need a lot of time for, covering mass spectrometry. Maybe in future, I'm thinking to have two, what to say two workshop. One is like just basic theory, and then we can have advanced one, so how to analyze the data, which software is best to use, something like that. So some Jyoti is asking for unknown biomolecule organic compound, which one will be better? I think you can go for both of them. Okay, whatever is easy to like you have access, you can go for both, so both will be good. Okay, so ESI is also good and multi is also very good. So yeah, whatever method you want to use, it should be fine. Okay, so yeah, why in FTICR you need this much big size? Because you are having magnetic field. So magnetic field you see in NMR also. If you want to produce a very high magnetic field like 10 Tesla and all, you need like like suppose 10 Tesla, then you need some, superconducting material, right? And for having superconducting material which can produce, high magnetic field, you need to have some liquid helium and liquid nitrogen around that, right? So that is the same way in FTICR also. You need liquid helium and liquid nitrogen. So that's why this, and you have very big like you generate the very high magnetic field. That's why you need very what to say, yeah, size becomes big. Okay, so someone is asking what is covered in the third day of this workshop. Oh, third day we are going to cover, fragmentation. Okay, so there are a lot of things to, and also I will, yeah, like different example of fragmentation. So, like analyze the spectra and then talk about. But we are not going to cover the theory part. Sorry, we are not going to cover that data analysis part. Okay, like using some software. Okay, so FTICR is ultra high resolution and accuracy, and it is also paired with ESI. Okay, so ESI is ion source. Okay, so it is an ion source ionization. So this is excellent for proteomics, polymer, and complex matrix. So it is very sensitive, but also expensive and maintenance heavy. So it's not so easy. So yes, Jyoti. So tomorrow we will talk about practical, analysis of spectra. Okay. So, I already told about, mechanism of how ICR works, right? So, yeah, you have some receiver plate and you apply some magnetic field. And then because your ions will be moving inside, so image current will be generated. And that image current will give you some time domain signal, right? And then you will do Fourier transform and you will get the mass spectrum, right? So, please understand in FTICR, you don't need a external detector. You just, mass analyzer itself is enough, okay? Okay, so here is the example. So you can see this example. So some molecular ions are trapped in this mass analyzer. Okay, and now you see what's going to happen. It's moving or not? Oh yeah. So now you give the some radio frequency. Okay, you see what's going to happen. It is going to move, right? And then because it is moving, so this is your detector plate, right? So sometimes when it is moving and coming near to detector plate, then you will get some image current, right? And because of that image current, you will get some, voltage, right? And that voltage will be like, yeah, frequency based, time based domain, right? Frequency based, and then we will convert to time based domain. Okay, so different mass will move differently. Okay, yeah, Anisa, we will talk about tandem mass spectrometry. Okay, please write your question whatever. So if I don't cover it today, tomorrow I will cover it for sure. Okay, that's it. So you can understand you got the different voltage, and then that different voltage will give you frequency based, right? Then you can convert to time based, and then you will get the M by Z ratio. Okay, so yesterday I talked about this what you call resolution, right? So I was telling you that ICR has very high resolution. So you can see this paper in analytical chemistry. They have used 21 Tesla FT ICR mass spectrometer. So you can understand in NMR you just use how much? I think if you have 700 no 800 megahertz NMR, then you use I think around uh, 8 around 7 to 8 Tesla, okay, magnetic field. But here you see they have used 21 Tesla magnetic field. So it's very strong. So in this paper, I would like to highlight this one. You see this one. So I don't need to, I think, explain also. So M by dm, this delta M, this ratio is 2 million, right? So it's more than 2 million. So what I mean by resolution, when you expand this area, you see, you get all the peaks. You understand? You get all the peaks. So yeah, it's yeah, so it's see here you have like some, they have shown some isotope also, right? So it's very interesting. So if you get some PhD or postdoc position in such field, I think you should just go, okay, because yeah, it will be good for your career. Though, yeah, if we come back to India, I'm not sure in India we have FTICR or not. So it may be hard for us, but yeah, it's good to, have the knowledge of such instrument. Okay, so in Orbitrap MS is also, yeah, we already talked. So it's a smaller, right? It's not so big. So it is also high resolution like FTICR, but more compact and user friendly, often combined with ESI and APCI, and dominates in metabolomics and drug discovery and proteomics, and also known for stability and ease of operation. Yeah, I already talked about this, right? So I can skip that. So here I want to show you some examples. So how it is actually analyzing different M by Z. So you see this one, this ring current, you can say frequency, right? So ring current we can say because of molecular ion. So you see single species, and this blue one is minor species. They are just, circulate, like in a spiral way, right? They are just rotating. So they are giving some signal, right? And here you have some impurity, right? This green one. So some maybe some contaminant is there. Okay. So this one is this one. Okay. So this, because of this molecular ion peak, which is rotating, you got this peak, and you can, because of this smaller one, you got this M+1 peak. Okay, isotopic one. But if you have some impurity, for example, sorry, you have some impurity, then you will get some extra peak. Okay. So in this case, you don't need a external, what to say, detector. Okay. So by this itself, the mass analyzer, you can have the spectra. Okay. So yeah, someone was asking me, QTOF and all. So I think it's, yeah, it's so you see. So ESI is electron spray ionization. So this is just the ionization method. And TOF is mass analyzer, right? And what is Q, right? This is very important. What is Q? So let's see. So Q1, for example, Q1, any quadrupole, it is selecting the ion. Q2 is called collision quadrupole, which will break the ion. And Q3 is analyze fragment. So it may be confusing. So let's look in the figure. So here, what I mean, suppose you have some sample and it goes through, you already ionize this and it goes, okay, and then you have some quadrupole, okay, you have some quadrupole here, okay, and this quadrupole, your sample, actually this is TOF, TOF, multi-TOF, right? So your you are just using some laser and sample is irradiated, and then some sample will be ionized and it will move, right? Let's move that. Okay, some sample will be moved and then it will go, and then you have this quadrupole. Okay, what will happen in quadrupole? In quadrupole we can select some molecular ion, right? Suppose you have M1, M2, M3, all that plus charge. So in first quadrupole, we can select this ion. Okay. So we just let this M1 go. Okay. Now this M1 plus, it reach in second quadrupole. Okay. Second quadrupole mass analyzer. Okay. So in this second one, this is, a small q whenever is written, it means this is collision cell. What do you mean? What do you mean by collision cell? So in this one, this mass analyzer, they have used a vacuum. Okay, they have used vacuum. So molecular ion will not be defragment. Okay, so please, sorry, not defragment, but fragment. Molecular ion will not fragment. But in this case, they are passing some gas. We are passing some gas. So what will happen when this molecular ion comes to this collision cell, which is Q, a smaller Q, right? So what will happen? This will be fragmented. So that's why this is called, CID. CID means collision induced dissociation. And there are actually variety of different name. So yeah, let's focus on one. So this is CID. So we call it, this is a CID chamber. Okay. Okay, so you see, in first quadrupole, what we did, we select one, okay, and then we send it to another quadrupole. Okay, it comes here, and then we used some gas which will hit on, because gas is coming, and then it will hit, so it will be just fragment, and after fragment, if you have one more quadrupole, then it will be called triple quadrupole. Triple quadrupole. Okay. Oh, I'm sorry if I'm not sure if my spelling is correct. Okay, so if you have triple quadrupole, that is possible. Okay, so then again you will be analyzing mass, and then it will go to detector. Okay, but in this case, there is no third quadrupole, but you have third TOF. Okay, you see you have TOF, so that's why this name is ESIQ-TOF. Okay, so I hope you understand. So okay, so yes, recording will be available. Okay. So yeah, I already told. So collision quadrupole we will denote always in a smaller q. Okay, so please understand. Okay, so it is always between q1 and q3. Okay, but sometimes this q3 will be replaced with TOF. Okay, so you don't need to worry about that. Yeah, it's actually because q3 will be used for analyzing that fragmented ion. So that's how it works. Okay, so what is the purpose of this, this kind of fragmentation using this, collision-induced dissociation? So fragment the selected ion by colliding them with inert gas. Okay, so yeah, that is and then we can study them. We can detect them and study them. What was the molecular weight and all, what spectra you got. So this is useful for, this, what you call, what is the name? Yeah, I forget about it. For proteins, in proteomics and all, this is very important because when we have, suppose protein is there and they have some polypeptides, and those polypeptides are made of amino acids. So, overall, all the proteins, they have this 20 amino acid, right? So if we just look at the protein, we may not know what amino acid was present, right? So if we use this, triple quadrupole, and we use this collision quadrupole, smaller q1, then you can fragment, and then you can send them to get the mass spectra, and you may get what kind of, polypeptide was there, what kind of this, what you call, amino acid is present in your protein. Okay. Okay, so yeah, I already told this, so let's move. Okay, so next is secondary ion mass spectrometry. So it is also called SIMS. So this is actually a surface analysis technique. Okay, so in this case, what we are using focused ion beam. So you see here, we have some primary ion, okay, and they are hitting on some surface, okay, sample surface. So what will happen? Some of the molecule will be leaving the surface, and they will just get ionized. Okay, and then they will ionize, they will move to mass analyzer, and then you can study, okay, what kind of, so what is the benefit of studying this? You can know what is the on the surface. Like suppose you made some thin film, like you make some device, and you have made some thin film, and you want to know what kind of element is present. So you can use this, like what kind of, um, if you can combine this with mass spectrometry, you can know that what kind of organic molecule is present, right? Sometimes, like you make, suppose, cough or moth. So in those materials, you make thin film, then it's, difficult to study them, right? Because we may have sample very less, so we cannot do NMR maybe, suppose. So you can just use this method, and just directly you can use your sample on that substrate, and then yeah, hit with the primary ion beam, and then you can know, your mass spectrometer will analyze the sample, and it will tell you what peak is coming, and then you can understand, using some online software like mass bank and all. You can understand what kind of material, what to say, uh, organic molecule is present or not. Okay. Okay, so primary ion beam will hit the surface, and then atom and molecules will be sputtering, and then some of the, because this is very high kinetic energy, so some of the molecules will be ionized, And then your spectrometer will analyze those ion based on M by Z ratio. Okay, so what is the application of this? Application of this is, in elemental and isotopic analysis, and also trace detection, because it can detect even ppm level. Okay, ppm level is like, suppose you have some sample which has 99% is maybe some other thing, more than 99% some other things, and less than 1% is your some trace moiety, that can also be detected. Okay, so part per million and also part per billion, so it's very less. Like out of 10 to power 9, you can say moiety, maybe one moiety you can detect, something like that. So also you can know the depth profiling. So profiling means, like, suppose first like on top surface was whatever was there, and you analyze, and then again you can remove that top surface and you can analyze what is in below one, and then again you can analyze what is below that. So it's very important, right? So yeah, that is the purpose. So there are various types of sims. So static sims. So static sims means it will just do the top one. So it will not, this laser beam is not moving. Okay, so it just analyze the top surface, maybe here. And dynamic one is like depth profiling. So it can do the, like, it can move and you can do at different surface. So you can know what is the chemical composition. So also there is a TOF SIMS. So it can do the high resolution molecular imaging. Okay. So, all are, yes, kind of similar concept. Okay. So this is a time of flight SIMS. Okay. So you see you have ion gun. Okay. And then it will be focusing on the beam. And then you see this is your surface. And then your ion will, your ion will be generated, and then they will be detected by detector. Okay, so you will get some spectra. Okay, so it's very, yeah. So in this case, instead of using laser, so in multi top we are using laser, right? So in this case we are not using laser light, right? We are not using light, we are using ion gun. Okay, so you should understand what is the difference between TOF sims and multi top. Okay. Okay, so here I have written, yeah, something. So what is TOF SIMS? So a high resolution surface analysis technique that uses short ion pulses and a time of flight analyzer. Okay, and it will measure the time ion takes to travel to the detector, which will help in determine their mass to charge ratio. Okay. Okay, this is same thing I told. So primary ion pulse will be bombarding the surface. Secondary ion are ejected and accelerated. Ions will travel through a field-free, as in time of flight, field-free drift region. Okay, which is this one, right? And then lighter ion will arrive first because they have more kinetic energy. Heavier ions takes longer. And because of this only, we are using this reflectron. This is called ion mirror also. So that kinetic energy will be balanced between them. Okay. So detector will record M by Z spectrum based on flight time. Okay. Okay, extremely high mass resolution. We can do the chemical imaging. That's very advantageous. Okay, sometimes when we make thin film in our research study, yeah, we want to know the what is the surface, how it is made of. So it's very important. So it is sensitive to organic molecules and fragments also. Okay, so someone was asking what is tandem MS. So tandem MS is actually, it's just we can say tandem is like two MS. Okay, MS MS. Okay, so okay, so what's happening? So you have suppose generated some ion, okay, and then you send them to the mass analyzer, okay, and when you send your ion to the mass analyzer, okay, after analyzing them, so you have different mass, right? Different mass and charge ratio, M by ratio, okay, and then it is going to the detector, okay, it is going to the detector, and then you will get the mass spectra, different mass, right? Okay, this is a simple mass spectrometry. Okay, what's happening in tandem? In tandem, you have ion source. Okay, so this is very important. Please understand. So you have first mass analyzer. Okay, so you got all of them ionized, and then you will send them to. So you see, you have two mass analyzer. Okay, in a tandem mass spectrometry, you have two. So first you ionized, and you send them. And now we select in first mass analyzer, we select for one mass. Okay, this one, red one, and then you send them to this one. This is normally, generally it will be, quadrupole. Okay, so as I told in, qtop, right? So in quadrupole, what I mean, you have some quadrupole. Okay, four, right? You have some four quadrupole, and you are passing some gas. Okay, some gas. So when your molecular ion peak will hit on those gas, then what will happen? This will be fragment. And because of this fragmentation, you will get a smaller fragment ion. Okay, you see, you got many. Now you again send them to next mass analyzer. Okay, and then what will happen? This mass analyzer will again scan them, and you will get again this mass spectra is for this one only. Okay, this so I can say this one. Okay, this one only. Okay, so what I want to say here, if you just use detector, so you may get peak for, this one, and then you may get peak for this one, you may get peak for this one. Okay, and also you may get peak for this one. But in this case, in this next mass analyzer, what you are going to get, you will not get these peaks. Okay, please understand, you will not get these peaks. You will get only peak for this molecule, molecular ion, and if it is fragmenting, then only. Okay, I hope you understand. Okay, okay, so yeah, so you have this MSMS, right? That is just a tandem. So as I told, so Q1 is just, mass analyzer, which is based on quadrupole type. Okay, so Q1 will filter one ion. Okay, and then a small q, whenever we write, it means collision cell. So it means some gas or some, some moiety we are passing in that, so that that ion will be fragmented. Okay, that's why it is, so it will collide and it will break into fragments. Okay. So Q3, as I told, scan fragment ion. So, just what I told earlier. So same concept. Okay, so what is the purpose of MSMS? So it will identify a structure. And for example, if you have this protein, it can sequence peptides also. And also it can confirm your compound. Okay, so I told you already, right? So if suppose you have proteins are made of polypeptides, and those polypeptides are made of amino acid. And if you just do mass spectra for, this protein, you may not get the what kind of amino acids are present. So you have to use MSMS. Okay, Sahas is asking what is the advantage of using MSMS. So as I told, if you have protein, you do the mass spectrometer analysis. You may not get what kind of amino acids is there. You understand? It's very large. Protein is very large molecule, and you are large polymer, we can say, and you may not get fragmented your protein so much that you get to know what kind of amino acid was present. So what you need to do? First, you use MSMS, okay? And in MSMS, in between, there will be fragmenting chamber, like a small Q. So there your some selected molecular ion or fragment ion. We can send them to fragment this fragment chamber, that where, your molecule will be fragment again, molecular ion will be fragment again, and then we can understand better whether, what kind of what to say, amino acid was present in that protein. Okay, so yeah, so what is the application of MSMS? You can use it for peptide sequencing, metabolite identification, structure elucidation, quantitative analysis in complex mixture. Okay, so if you want to use the Uh, okay, so if you want to use the MSMS for proteomics, so protein is very large, size, right? So first you have to do digestion. Digestion is like break down the, some, like break down the some bonds. Okay, and then protein will be digested and it will change to peptides. Okay, peptides, and then you use this MSMS. Okay, so we don't need to use directly like make send this sample to mass spectrometry, first you have to break them, okay, because it's very big. You have to break them and then yeah, change it to peptides. So digestion is like use some enzyme or other method also you can use. So for enzyme people use like trypsin for example. And then these peptides you can send it to MSMS and then it will fragment ion and then we can know what kind of sequence was present. Okay, so digest protein first and then use the, send it to MS quadrupole one and then select the peptide ion. Okay, and then we will send that selected peptide ion to collision cell where it will be fragmented. And then it will again go to another mass analyzer with quadrupole 3, right? And then it will detect fragment ions. Okay, so that is the advantage we can use for knowing what kind of amino acid sequence is present. For example, you have peptide with ALKGF, okay, different amino acid, and you suppose fragment these. So what you are going to get? Suppose you can get B1, B2, B3, B4. With these all are having N-terminal fragment, okay? So if you know amino acid, you must be knowing what is N-terminal. And other possibility is Y4, Y3, Y2, Y1, which is carbon terminal fragment. Okay. So okay, you can use it for amino acid sequence. Also, you can use it for identifying post-translational modification. It's for proteins only in our in any cell. Okay, so yeah, you can also use it for metabolite identification. So if suppose you have some metabolite, you extract metabolite from sample and then you send them for MS with quadrupole one. Okay, select ion of interest, whatever ion that you think, oh, it's very important, and then send them for fragmenting in the collision cell. And then select after that, you select some of the fragmenting ion and then send them to mass analyzer third, okay, Q3, and then you record the fragment ion. So, and if you whatever data you get, you can compare with online software like Metlin, HMTB, okay. And if suppose some metabolite which is already reported, you can know, oh, that type of metabolite was present, okay. So okay, so you can learn about molecular structure, isomer conformation, and also pathway tracing and drug metabolism. Okay, it's very important. So where we can have applications, so drug discovery, biomarker research, clinical diagnostic, and also we can apply in a plant food analysis. Okay, this is the, I think, yeah, you will understand better. So just watch this video. So this is a tandem mass spectrometry, right? So you have some protein which has polypeptides, right? So any protein has lot of polypeptides, and these are all amino acids. Oh, oh, someone is saying not audible. Ah, okay. I don't understand why. 1 minute. I think, okay. Okay, okay. So I think I have to. So I think, yeah, you can watch this video. So I also feel my voice is low. So yeah, just watch this. So if yeah, you find some problem, just write it down. Okay, so I know it. It was not audible, so I thought, okay, what is the problem? So purpose is, yeah, what I want to show. Okay, so what I want to show here, yeah, see, so some ions are moving. Okay, so from mass spectrometer one, which is just like different mass analyzer. Okay, so you can say quadrupole type. So you say, and in collision induced cell, you have some inert gas. So what will happen? Your mol fragmented ion or molecular ion, they will hit on the this inert gas. So what will happen? They will be fragmented further. Okay, and then they will move to mass spectrometer 2. Okay, and then we can like select them. Okay, So you see in a fragmented that what to say, if because of fragmentation you can have different kind of broken bond, right? So similarly you can know the different structure. Okay, so what I want to say, we can know the what mass to charge ratio of your amino acid is there because of this polypeptide. So yeah, then you can have this arginine, like whatever amino acid is there. You get mass spectra for fragmented ion, and then you can get the what kind of sequence is there. That's why we call it what kind of polypeptide sequence is there. Okay, so that is the method. So and you don't need to do this by yourself. Okay, so you can use some software. Okay, so okay. Okay, I think I will now almost I'm done. So please write if you have more question, please write it. So maybe I will talk about this myoglobin, I think tomorrow. Hello? Oh, am I audible? Okay, okay, okay. So if you have any question, please write. So yeah, someone is asking which software is used for LCMS. So actually, there are many software that we can use, but yeah, we should find something which is, like a free software, right? So yeah, then it will be easy for us. So yeah, you can go for this MS dial. Okay, maybe I will send you the link. So you can try, yeah, you can try. 1 minute. So yeah, Vidya is asking why argon preferred for ICP-MS. So you see, in ICP-MS, tomorrow I will talk about ICP-MS. So in ICP-MS, argon will easily, generate the plasma. Okay, so that's why people use argon. Okay, so I will talk about ICP-MS tomorrow. So I wanted to complete today, but I think today it is not possible. And then we have, Okay, Sahas is asking something. I have extracted cell-free supernatant from bacteria. I would like to characterize metabolites present in cell-free supernatant. I have performed LCMS. I have got only high molecular weight compound. Why small molecular weight compound have not been detected in LCMS? So, okay, why small molecular weight? So it might not be there in your, compound. Maybe that is the reason it is not detected. And other thing could be when you are doing LCMS in starting, please make sure that your this liquid chromatography setup is not starting what to say starting molecule or analyte. It is not just putting in the what you call in like uh, waste solvent. Okay, so sometimes what happens in LC is that in starting, if when we are starting our liquid chromatography setup, maybe some solvent is just passing. So if I'm not sure in your setup how is that. So it might be, or other thing could be your this what you are saying, a small molecular weight compound. Maybe it is very polar, so it's not coming out. So yeah, you may have to change what to say, maybe your solvent or something, and then check again. Also, sometimes what happens is when you have this, like you used like some kind of purification method, and in purification method you have used very polar solvent. So maybe your smaller molecular weight compound, it is just dissolved and it is disappeared from your sample. Okay, so that could be also another possibility. So yeah, so I will suggest you to whatever, like if you do centrifugation and all, suppose say whatever decant you are getting now, so you should keep it, okay, and do LCMS for that one, or just check. Yeah, I think this mass spectrometry is best. So Sahas is asking, LCMS could detect a small as well as large molecular. So LCMS is what to say. Mm, LCMS. So you see, problem that I am thinking is happening is if you are using very large molecule and you are trying to pass through LC, liquid chromatography column, it may not pass actually. Okay, so sometimes for polymers and all, yeah, it's difficult to pass through liquid chromatography because that column is made of a stationary phase, which is mostly silica, or it could be opposite like non-polar. What to say? It is RP, right? So reverse phase, right? So uh, even then, yeah, passing large molecular weight like polymer and all, yeah, it may not even pass. So I'm not sure. But in your case, what you are saying is you are detecting the large size, you are not detecting a small size. That's very interesting, actually. No, 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 no. It's not necessary to be compound to be UV active. So I wonder why you ask that. For LCMS or GCMS, we don't need any, worry about UV active. Okay. UV active is just, for detecting, what to say, for detecting molecule in a liquid chromatographic setup. Okay, for mass it doesn't matter actually. So what which method would be approved for analyzing what type of metabolized percent in I think go for this Malditov you can go. Okay, and also this ESI method you can go. Okay, so okay, so I think I will stop for today, and tomorrow let's meet again. Okay, thank you everyone for your time. So see you tomorrow.